Yeah, this afternoon we'll have two research seminars. The first one is by Michelangelo Preti. And okay, I guess you can go ahead.
Okay, thank you. Thank you, obviously, to give me the possibility to present this work here. And I'm trying to convince you that we have a new method that we call ABBA to solve the BFKL regime in n equal 4. This is a paper made in collaboration with Simon Ekamar and Nikolai Gromov and some other ongoing work with them. Okay, so let me give you some context of this work. This is another generated picture, obviously. So the context is starting from very different topics. So conformal range theory, n equal 4 QCD, integrability, BFKL, hadron scattering. There are many different stuff on play. And what I'm trying to do is we build a new environment that we call indeed ABBA. That is an acronym for asymptotic Bethe-Baxter ansatz. That actually describe the connection between all of them. And I will be hopefully not very technical at the beginning, and at the end a little bit more for the expert. So stop me whenever you want, obviously, if you have questions. I will start from very early, so some pre-QCD physics, namely range theory. This is an environment in which we describe hadron scattering. But what I don't see you, so what is going on? Hello?
Hello, yes, Michelangelo.
Okay. Fine. Okay, so
sorry, just to are you changing slide or you are still on the first?
I am.
I don't see you changing slide.
Yeah, me neither.
So you are still in the title one?
Yes.
Yeah.
Okay, now I see your screen. Yeah.
You see me changing now?
No.
That's weird.
So you had the second slide and third slide with this ABBA. I see. Now it makes more sense. Sorry, maybe it's simpler if you export to PDF or something.
There is an animation, so this is why I didn't export.
I see. Maybe you can just do from here full screen instead of play.
Yeah, but it's not going to work. It's showing the. Yeah, you'll see.
I think when you get to the animation, you can go back to the screen without or.
Let me try to do something like this.
Yeah, that looks.
That's fine for you, or?
Yeah, I think it's fine.
It's not too small?
No. I mean, I see it big.
I'm sorry for it, but yeah, I was expecting that you could see.
It's okay.
Okay, fine. But about the context, yeah, when I was talking about context, I was here and with the other generated picture. And the acronym is this ABBA, asymptotic Bethe-Baxter ansatz that I was mentioning. And like what I'm trying to do is to put all those topics together, n equal 4, QCD, BFKL, integrability, conformal range theory, etc., to solve this BFKL regime for a general twist in n equal 4, okay? So I'm starting from the beginning. Like, obviously, there are no animation anymore now, so it's a bit a mess, but it's a big mess. Yeah. So it's not going to work like this. Anyway, I'll try to make it work, but it's not going to work because there are some stuff on top of each other, so but you will see. Anyway, I'm starting from pre-QCD physics, so range theory, and imagine
Michelangelo, but you could also just put the slides without the full screen. It's fine. We see if it's important to see the videos.
But you see, you don't see them like this. Okay, let me do one stuff. Let me export it and just one sec. Sorry for the annoying stuff. Sorry, guys.
It's okay, don't worry.
Okay, let me share again. And then we can skip the animation in one place. Okay, so I guess it's going to work now. Is it working?
Yeah.
Okay, so let's forget about all this stuff and then go back to the Regge theory. And imagine that you have two protons scattering, and the energy S is way bigger than the transferred one. And this is called the Regge limit. So S is way bigger than T, and there are some exchanging of stuff between the two hadrons. The interesting stuff is that those exchange particles can be recast in trajectories, what is called Regge trajectories. And this plot is alpha is the spin in terms of the mass, T. And for example, trajectories, let's say the leading one, for example, is this one, 0.45 plus blah, blah, blah. The first number, we call it intercept, and is where the trajectory is crossing the T equal to 0 point. And the second number is the slope, 0.9. And why this is interesting? Because the total cross-section of some scattering, like this one, for example, behaves like S to the power intercept minus 1, okay? So naively, one can say, okay, let me see which of these trajectories is the leading one. So the one with the biggest intercept is clearly the first one, and 0.45 minus 1. So it means that all this kind of hadron scattering, they have to behave as S to the minus 0.55. But this is not true, because from experiments, we know that the S behaves with a positive power. And interestingly, both in the case proton-proton and in the case proton-antiproton. So also for hadron-antihadron scattering, this is the case. So there is some kind of universal behavior here that wasn't understood in the early 60s. And the solution was made by Gribov in 1961 with the introduction of a new trajectory. Is a trajectory with intercept bigger than 1, with no particles on top, that was called Pomeron. And the intercept this time is 1.08 to match the data, and everything was fine. And this was the easiest way to solve the problem. And another interesting stuff indeed is that has to work, this new intercept has to work also for proton-antiproton case. And indeed, there is a famous theorem that is called the Poveranchuk theorem, where in the Regge limit, when S is big, the ratio of the two sigma tot, proton-antiproton and proton-proton, has to be equal to 1. So this is assuring that also in that case, the Pomeron, this Pomeron trajectory, is the leading contribution to the sigma tot. But another interesting property here is that even if the ratio of two functions is equal to 1, it's not true that the difference between them is equal to 0. So they don't have to be the same. They are asymptotically the same, but they are not the same. And indeed, in early 70s was predicted the contribution of another kind of trajectory similar to Pomeron, but this time with charge conjugation odd. The Pomeron one is charge conjugation +1, and this is a charge conjugation -1 in 1973, and this is called Oderon. And why this is important because while Pomeron was found in experiment from very early days, Oderon is a very sneaky kind of contribution. And indeed, many experiments try to find it, and you can imagine like a experimentalist trying to find the one ring. For 70, 60 years, they try to find it, and many experiments were connected together to match this difference. Some early project in CERN, some other stuff in Petra, in DESI. These are hypothetical one, and D0 in Tevatron, and in Totem in CERN more recently. And finally, in 2021, they managed to build some model to match data from Totem experiment and D0 experiment, finally finding this difference between proton, antiproton, the blue one, and proton-proton, the red one, scattering. And indeed, you see that the difference is outside the error bar, and finally they matched something that looks like an Oderon, okay? And so these are an important point, because looks like that this is a very old physics, this is a pre-QCD physics, but indeed is very big still in present time, because to find just the subleading term for those scattering, they took 60 years of measurements. Okay, so this is one of the motivation why studying reg physics is still important now. And the big deal is also from a theoretical point of view. Indeed, if you look at all this picture from a QCD point of view, you can imagine that when you have this proton-proton or proton-antiproton scattering, those exchanges, those exchange particle can be interpreted as some exchange of gluons. And in the gluon, the two gluon exchange, this looks like a pomeron. Is a C-even object, is a coronal singlet, so it looks like a pomeron. And the three gluon exchange looks like an Oderon, and so on and so on. You can go 4 gluon exchanges, 5 gluon exchange, and so on. And the big deal in QCD is that we can compute the asymptotics for those states. So we can compute this behavior as S to some power, and computing the expansion for some value of decoupling. And in particular, in the late 70s, the famous BFKL equation were made, where the two gluons exchange now are some kind of, they are called Regis gluons, because it means that we are summing all this ladder of transverse gluons. And the same was done in the 80s with the BKP equation for Oderon and so on, and for any other number of exchange of Regis gluons. The interesting stuff is that those ranks of the ladder contributes with some function that is very well known in QCD and is called BFKL kernel. Psi is the gamma function, and small gamma is the Eulero-Mascheroni constant. And so this looks like a Bethe-Salpeter resummation. So any rang contributes with this quantity, and the resummation of all of it is giving you the behavior of the high energy asymptotics, sorry. But why all of this is important to integrability in particular in my case, is because in the early 90s, Lipatov found that the effective Lagrangian describing all this business is an integrable Lagrangian. And lately was found an integrable spin chain that is describing all of it. And the point is that we have everything under control in N=4 from integrability point of view. We know a lot on N=4 from integrability point of view. So the question is, can we reproduce all this reg business in N=4 and see maybe if there is some comparison that we can make from N=4 to QCD physics. This is the main environment in which we are working on. Okay, cool. The point is that when we move from scattering theory in QCD...
So, Michelangelo, can I ask a question?
Sure.
Just maybe it's naive, but now I don't remember exactly. When they compute the BFKL, it's the problem, it's reduced to like a 1D problem in a way. Is that correct?
Yeah, I mean, like there are different ways. Like these in QCD, I honestly don't remember the exact computation. Is very early on a computation, but in the 90s when Lipatov made this computation, is just some kind of spin chain-ish computation. I mean, like if you're talking about the Regis gluon and these ranks resummation,
Yes.
it's not really made in a honest way, I would say.
I see.
This is also why people in more modern time, people working on light ray operators, etc., like, I don't know, Simon Carnot, they don't really like those pictures that they showed, because no one at the end made the actual resummation of this
I see.
But
Thanks.
let's say this BFKL Pomeroy eigenvalue is appearing everywhere in QCD and in any branches of Regge physics. So there are many different ways in which this stuff was computed, actually. Okay, so when we move to conformal theory, there are big differences between the amplitudes point of view that we had before. Indeed, the amplitudes are related to correlation function, and what we were calling mass T was equal to mass square. Now is the scaling dimension. The Regge limit is some like cone limit, and when we are looking at the leading trajectory, the one that is contributing to sigma tot, let's say, this corresponds to some trajectory that contains leading twist operator, so the operator with the highest dimension, okay? And the intercept, that is the observable that we are interested to compute, alpha of 0, now is a S of 0. So S is the spin. Sorry, I didn't tell you, but delta is the anomalous dimension of the operator we are considering. S is the spin. L is the length of the operator, so the R charge, if you want. And gamma is the anomalous dimension. And the intercept now is defined as S, the spin, as a function of delta, where delta is equal to 0, okay? And another interesting point is that what we were saying before, let's say where the intercept was important before, it was important in the computation of sigma tot. Now the intercept is appearing directly in the OPE decomposition. So there is also this comparison, and the OPE is encoding the information about the intercept of the trajectory we are considering. And in CFT, in N equal 4 in particular, there are many other features. For example, we can interpret like all those Regge trajectories as light ray operators. There are some horizontal trajectories, so not only like the usual trajectory that we see also in QCD, but also some horizontal one. That means that we have for a fixed spin, we fix a spin to be, I don't know, -1. And for a spin -1, the trajectory is taking all the values of delta from -infinity to infinity. And this is actually where the BFKL regime is. And then also there is a very important stuff that we will use later, that is the maximal transcendentality principle, that is assuring us that some part of the QCD result is actually encoded in the N equal 4 one. So we can compute N equal 4 Regge theory if you want, and our result in N equal 4 will correspond to some part of the QCD one, and usually is the maximal transcendental one. So imagine that you are expanding some power of the coupling constant, and the coefficient as an expansion in transcendentality 1, 2, 3, 4. Let's say 4 is the maximal one. The transcendentality for part of this result in QCD is the same of N equal 4. This is a good motivation why we are interested in studying N equal 4, because we can fix part of QCD, or not all of it, obviously. And let me give you some vocabulary of Regge trajectories. These are typical one. The black one is what you are expecting to have when G is equal to 0. G is the coupling, the Toff coupling. When G is equal to 0, trajectories are just lines that they cross at some point, and they have this kind of cusp. When G grows, the trajectories start to bend, and you see with growing G, they bend and they move up. So it means also that the intercept is moving up. Okay, but this is another story I will tell you soon. D-glap is we call D-glap this diagonal part. D-glap is the usual Altarelli-Parisi part on evolution, and this is why it's called like this. And this is the area in which there are the local operators. So on top of this line, on those lines here, there are local operators for different Gs. And for example, in this case, we are considering twist 2, so trace of some scalar, a complex scalar square. And the BPS object is on the axis here, and it's pretty clear because for different Gs, you see all trajectories have different Gs, they are passing through one point. So it means that this point has no anomalous dimension. I didn't mention, sorry, but probably you noticed that this is a spin plane in terms of delta. So it's the spin in terms of the anomalous of the scaling dimension of the operators. So when delta is exactly equal to 2, all the trajectory are passing there because this object is protected by supersymmetry. Then we know that there is some shadow transform, so operators are paired to their shadow partner in the other side of the graph, because it's a symmetric delta to minus delta. And then we have the infamous horizontal trajectory. This horizontal trajectory is where the BFKL live. So this is the BFKL regime close to this horizontal trajectory, and the horizontal trajectory goes from minus infinity to infinity and is spanning the whole plane. Okay. The intercept, as I told you, is the value of the spin for delta equal to 0. So is the value of those trajectory along this line here. And we have a couple of branch points. You can see here that for G equal to 0, there is a cusp. So we have a branch point there. And when G is slightly above 0, those branch points are moving from your laptop screen closer to you. So they are moving in the imaginary direction. And this make those trajectory bend. So, and more the branch points are moving away, more the trajectory bends, okay? And obviously those branch points build a cut up to infinity. And if you're passing through the cut, you go to many more trajectories. So any leading trajectory is connected to another infinite amount of trajectories that are subleading, okay, for any twist. So this is what we want to expect. And so what we expect is that for G equal to 0, we have some crossing of trajectories. And for G non-zero, we have some resolution. They bounce on top of each other, okay? Sorry. Cool. But all this business is made possible through some integrability technique. That the most advanced one that we know is quantum spectral curve. And why this is meaningful? Because it's encoding a lot of different aspects of integrability in N=4. Indeed, there is this ABA. ABA is an older technique for local operators. Is a perturbative kind of technique, and is exact up to wrapping, so up to some power in G that depends on the twist of your operator. So you can expand exactly up to, for example, for twist 2, up to G to the 4, and everything else is not known. BFKL is very different because it's totally non-perturbative, and in principle, you have to resum an infinite amount of terms that behaves like this. So you see that ABA for local operators and BFKL for this horizontal trajectory are kind of orthogonal aspect of integrability. But QSC, quantum spectral curve, is merging them all together because it's an environment in which we can perform a non-perturbative computation numerically at finite G and interpolates between diagonal trajectory, DGLAP, and BFKL. So BFKL is the horizontal one. The ABA, let's say, is the part that is relevant for the diagonal one. And with quantum spectral curve, I can interpolate between them very nicely, okay? So I don't want to go to details here, but just sketchy. You imagine QSC as a box with a lot of stuff inside. We input some quantum number of the operator that we are interested in. J1, J2, J3 are the R charges. Delta 0 is the per dimension. S is the spin. S2 is the second spin, the conformal spin. Those are the charges for PSU, the symmetry group of N=4. So we input it inside the box. We shake the box, and we have as an output the dimension of the operator in terms of the spin, or more convenient in our case, because in the case of Regge trajectory, it's more convenient to have S in terms of delta. We can compute S in terms of the anomalous dimension delta, okay? Just for the expert, if you open the box, there are some auxiliary function. Those are the functions that also Andrea was mentioning, so the Q function. There are 256 Q functions, and there are some relation between them. Those relations are actually, they have to be, we have to add to this set of QQ relation their analytic properties, because indeed they live on a Riemann surface, and we have to know how they connect between different Riemann sheets. The only important stuff that I want to say here is that you see from this sketch that the cuts present in this Riemann surface they have some very specific length that is related to G. So the TOF coupling enters in the business of quantum spectral curve integrability just as the endpoint of those cuts. So this is the only place in which is encoded the information of the TOF coupling. This is pretty interesting. And also, we can close the system of equation adding this gluing condition. Gluing condition means the condition in which some Q of the first sheet, for example, is equal to some Q of the second sheet through some matrix. And this matrix is the gluing matrix, that in this case is not just a number, is a function of this parameter U, this complex parameter U, because we are performing analytic continuation in spin. And when we perform this analytic continuation in spin, we have to have this matrix, not just a numerical one, but has to be function of U. Is an auxiliary variable, okay? This was just for the expert, like this box in action means that, for example, if we go to SL2 sector, so operator of this kind, trace of derivative plus power S, the spin, and some complex scalar Z to the power L. L is the twist. So those are quantum numbers. We input those numbers and we can have some output numerically, for example. This is the example of the Konishi one. So L equal to 2 and S equal to 2. This is the Konishi operator that is matching very nicely the string theory predictions and the perturbative wave coupling predictions. So this is the powerful environment of the quantum spectral curve. And the box actually exists. This photo was made in King's College, so can actually be used and it exists indeed. Cool. So let's see what quantum spectral curve can do in our context. So for Regge trajectories, I told you that those Regge trajectories are connected, leading one and subleading one through some branch cuts, etc. So we can see the full Riemann surface that they encode, looking at numerical quantum spectral curve. So we can move in the imaginary side of delta, the real part of delta, just move in the parameters, and we can build the whole Riemann surface. For example, for L equal to 2, that means a trace of Z square, if you want. This is the operator that you are starting from. You can see this kind of picture. And if you slice the picture in the real plane, so you see here this 0. So if you cut the picture in the real plane, you see the Regge trajectories. So those are the actual Regge trajectories. The black one is the leading one. The blue one is the first subleading one, and so on. There are many more. There are some important stuff to say here. One is you see G. I hope that you can see the font is not very big, but different trajectories of the same color have different G. And when G goes smaller and smaller, is approaching the horizontal line, like I was saying before. And you see that when the black one is approaching the horizontal line here, the blue one is approaching this triangular part here. So at the end, on the horizontal trajectory, this infinite length object here, just one trajectory at the time will be there. So there is degeneracy 1. So the horizontal trajectory has just one Regge trajectory on top, okay? And if we expand in coupling, we see that S plus 1, because remember, this is S as a function of delta. The horizontal trajectory is at -1. So S plus 1 goes as G square times some function. And this function is exactly the BFKL Pomeroy eigenvalue. So this is interesting because you can see that computing from quantum spectral curve technique, integrability techniques in unequal 4, this Regge trajectory for twist 2 operators, the simplest one, you just find the QCD Pomeroy, exactly the same. At leading order are exactly the same. At subleading order, just the maximal transcendental part is the same on QCD. So this is the point of connection between N equal 4 and QCD, and why we are indeed interested to explore this Regge business. And obviously, you can go higher, expecting to find some kind of Oderon stuff or Oderon-like objects. You can go to L equal to 3. L equal to 3, the Riemann surface is a bit more complicated. There are 3 sheets now that are planar all close to the branch cuts. And indeed, if you cut along the real plane, you see there are 3 trajectories and many branch cuts, branch points, and the branch cuts is starting from there to infinity, that are moving away. You see from the real plane. This is the real plane, and the branch points are away. And if now G is 1/2, if I'm reducing G, those points are approaching those lines, those trajectories, for example, here. You see that the lines are approaching more and more the horizontal one. And this case is a bit different respect to before, because you see on top of the horizontal trajectory, when G goes to 0, for example, here, the blue one and the orange one will be degenerate. And the same stuff, the green one and the orange one will be in the second segment here, and so on and so on and so on. So the horizontal trajectory has degeneracy too. So 2 regge trajectories are on top of it. And if we expand as before, this time the horizontal trajectory is at -2, because it's depending on the twist, the position of the horizontal. This time then S plus 2 is equal to plus minus 2G. So we have 2 solutions because we have degeneracy 2 trajectories. But the important stuff is that, one, the leading order is independent on delta. That is pretty peculiar and unexpected. And second, more importantly, is linear in G. And this is very weird, because usually integrability computation are given as a function of G square. So you don't expect something that is a function of G instead of G square. So something is going on for sure. So to explore this stuff, we move to L equal to 4, and we want to explore more and more and understand what is going on. And this was an animation just to show you the Riemann surface, but we can skip it for the moment. This is the Riemann surface for L equal to 4, way more complicated. There are many more trajectories, as you can see on the real plane, and many more branch cuts. You see the very involved Riemann surface. But if we cut the real plane, this is what we see. We see some operators, the BPS1, trace of Z to the 4, here, like before, as expected, on the blue trajectory. Then at spin 2, instead of having just 1 operator, we have 2, because there are 2 trajectories with 2 operators. And then 3 for spin 4, and so on and so on and so on. So there is an infinite amount of trajectory passing through here, but just few of them are bending. You see just the blue one, the orange one, and that's it from the first slope. Then there are the purple one that is bending from the second slope, and so on. And some of them, like the red one, you see the red one here? The red one go through, blah, 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 and when it's approaching the horizontal trajectory, is passing through. So it's not bending anymore. So the point is that we have to find also a selection rule on how many trajectories are bending, why only, in this case, for example, just 4 of the infinite amount of trajectories we have are bending on top of the horizontal trajectories, and why other are passing through, like they don't have a branch cut, they don't have a branch point, so they don't see the branch point here. And you see indeed, in this first BFKL area, we have 4 degenerate trajectories. In the second one, again, 4, and so on. And the 4 is repeated for the all horizontal trajectories for the first one. Because in principle, you know, I told you there are an infinite amount of trajectories, so there is an infinite amount of horizontal trajectories too. So this is just the first one, okay? The leading one, if you want. Okay, so we can compute the intercept, for example, there. So we expect to have 4 of them. And indeed, this is the non-perturbative expansion in the coupling of the intercept. And again, we see some peculiar stuff, because the blue and green one, they behave looking at if we fit the data and we check the behavior in G, we see that the blue and green goes as a function of G, and the other 2 are as a function of G square. So it's a mixed situation of the 2 that I explained before. So L equal to 2, twist 2 was just a function of G square and 1 trajectory. Twist 3, 2 trajectories and just function of G. Twist 4, they are 4 and they are mixed. So they are both G and G square.
So Michelangelo, I have a question. Just to understand, when you have the generate trajectories, at input in the quantum spectral curve, you still input non-degenerate data.
Yes. Kind of. Let me say in a better way. So when you want to explore, if you don't know anything about this horizontal area, you don't know anything about it. So you don't know where it is. You don't know, you know more or less that, for example, in this case, twist 4, we are expecting to find it around spin -3. And that's it. So what you do is, let's check where the local operators are. We go in the local operator point, and then we continue. We do the analytic continuation in S. And so we start to move to find where the trajectories bend. And then at some point, some of them are bending, some are not. And so this degeneracy, you find it like looking at how many trajectories are bending. This is a numerical way. Obviously, we have a way that is more systematic and is a theoretical, analytic way that I will show you in few slides. But then you start from a single local operator and you go down. But obviously, for a same spin, there are many local operators, but any of them belongs to a different trajectory. So you start from non-degenerate object in a single trajectory, and you find the trajectory on the horizontal one that can be degenerate with many others.
I see.
Okay. Okay, so let me recap a little bit because there was a lot of information. So we have from numerics, twist 2, 3, and 4. Those are the Riemann surfaces. We have this degeneracy on the horizontal trajectory, 1, 2, and 4. Some intercept data, and then some weak coupling data that we know from the literature. The first line here is known by years, and this is our result in the collaboration with Rob Klabbers and Istvan Chesney in the paper of twist 3. All the rest, we don't know anything. So what we want to understand is indeed if there is a systematic way to know everything here, up to some wrapping, up to some point in which the asymptotic approximation collapse, okay? And so this is the whole philosophy of the ABBA, these asymptotic Bethe-Baxter ansatz. And the point is taking QSC, this very complicated set of relation and analytical properties, reduce them to look like some asymptotic Bethe ansatz, but with an additional information that is given by a Baxter equation that we can solve exactly. So now I can go a little bit more technical, but just to give a glimpse of what is going on. So those Q functions that I was mentioning before, they have some monodromy because they can connect between different sheets of this Riemann surface. This monodromy is called omega. And then looking at the scale of this omega, we can simplify the QSC equations. Simple like that. This is the philosophy of ABA, for example. And then once we are simplifying this equation, we can look at mu AB, that is the monodromy of another set of Q function that we call P. And looking at mu 1, 2, we can check where there are some roots, and those roots are momentum carrying roots, and we can build the dispersion relation. And this philosophy was applied for local operators with ABA, asymptotic Bethe ansatz. The dominant part of the monodromy was omega 1, 2. And then looking at the momentum carrying roots, one can build the very famous dispersion relation for magnons. That is ubiquitous in integrability papers, okay? And is the energy of the related spin chain, for example. In our case, is a bit different because in ABBA case, the dominant term in this BFKL regime, so close to the horizontal trajectory, the dominant part of the monodromy is not omega 1, 2, is omega 1, 3. And this has a lot of implication. Indeed, there are 4 additional roots that we call ZK on top of this mu 1, 2 monodromy of PA that I was mentioning before. And with those roots, we can build a new dispersion relation where S plus L minus 1 plays the role of the energy. So the horizontal trajectory S plus L minus 1 is the energy. And we can build a new dispersion relation that, interestingly, is massless. So it's a very different kind of object, and it's very similar to what is happening in DS3, where massless dispersion relation plays an important role. Okay, so now, like for some of you, if you want, you can close your eyes for a moment. I can show you some bad, horrible formulas. Because in this simplification with omega 1, 3 dominant, some Q function are playing a bigger role than others. And 3 of them can be written in terms of some dressing phase and the new roots, zk, and the dressing phase sigma is a new one, different from the ABA one. And one of the Q function is solution of the famous Baxter equation. Why this Baxter equation is important? Because one, we can solve it exactly, and this is part of the motivation why this ABBA works as a charm. And second is the all loop generalization of the famous Baxter equation that Lipatov found when he was finding integrability of the BFKL regime, okay? This is the same equation, but all loop exact. And then looking at the gluing between different Q functions, you can build this equation. This equation is the ABBA equation, actually, for the first horizontal trajectory, where this sigma part contains the dressing phase, this kappa part contains the collection of all the roots, and this G part is a kernel with some gamma function. This is not very important. It's just to show you what actually ABBA is. It's just this equation plus some additional information from the Baxter, okay? And I can give you some example. When we go very close to G equal to 0, so very weak coupling, that equation simplified drastically. So the dressing phase is going to 1. These other additional theta, and that is not important to mention now anyway, is going to 0. And the equation is just 1 equal Iz to this power, where L is the power of the operator we are looking at. So operators that are in the trajectory we are looking at. So the solutions are pretty easy. Indeed, those are the roots of the unity. And they are parameterized by this number, nk, that goes from 1 to L plus 1. Then there are some additional constraints that I'm not going to mention, but anyway, there are 4 solutions. 2 of them are related to the 2 other. And then there is another selection rule that tells you that N1 plus N2 has to be even. So given that, we can solve the whole system, because indeed, knowing now the solution that are those Z, this exponential, and plugging everything inside the dispersion relation, we know that S plus L minus 1, so the horizontal trajectory, goes as 4G times this cosine. Cosine on pi N1, blah, 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 plus cosine pi N2, blah, blah, blah. And then we can go higher and higher. So if you expand the next to leading order of the dressing phase, for example, you find the G squared term, and so on, the G cube, G4, and so on. We can go infinitely amount of them. But there are important stuff to say. The G squared term is where the first time the dependence on delta appear. And the dependence on delta is just encoded in the BFKL Pomeron eigenvalue. So this is very interesting because this is true for any L. So for any L, we know that the G squared term is proportional to the BFKL eigenvalue, and that's it, the QCD one. Another important stuff is that the leading term, the one proportional to G, is independent of delta, like we saw, if you remember a few slides ago, for twist 3, I showed you that there was the result, the leading term was independent on delta. And this is true universally, so for any L. And then obviously, remember, this is asymptotic. So this expansion works up to G to the power L plus 2. So if we go twist 4, for example, this expansion is exact up to G to the power 6, excluded, okay? And another important information that this equation is giving is the degeneracy, because given the solution and those selection rule, we can check how many possible roots we have. For example, let's take L equal to 2. L equal to 2 means that N can be 1, 2, and 3. And so you see, like, let me say in this way, like it can be 1, 2, and 3, but since N1 plus N2 has to be even, 2 cannot be considered. So has to be N1 has to be equal to 1, and N2 has to be equal to 2, 3, okay? And this is represented in this way by those diagrams. So this is, for example, N1 equal to 1, and 2 equal to 3, and the related one in the other side of this unit circle. But this means that this is the only possibility that we can give to that we can have for L equal to 2, and this is giving the degeneracy. So there is only one choice. For L equal to 3, there are 2 choices, and so on and so on and so on. And this is reproducing the degeneracy of the horizontal trajectories. Plus, looking at the leading order, we can also, just with those informations, we can see why some of the intercept were going as a G square and some of them are going G. Indeed. Let's say, let's cut this circle with a line here, this symmetry line passing through the middle here. You see that the roots are symmetric, so they are related with a minus. And so if I'm inserting everything inside here, there is a cosine of something minus a cosine of something, the same object. So cosine of alpha minus cosine of alpha, so the G, the linear term in G is not present. So we know that for L equal to 2, the intercept will, and the BFKL regime behavior will start from G square. And we can do the same for the other one. So this y for L equal to 3, we have the linear term, and this y for L equal to 4, we have two solutions with the linear term and two solutions with the G square term, okay? And you can expand it up to the L you want, obviously, because there is no limit to it. And let me recap from for what we saw before. So we had degeneracy 1, 2, and 3. Those are the solution of the ABBA up to the power that is still exact. And two solution plus and minus for L equal to 3, for solution plus and minus those one, and the two starting in G square. And those are matching everything we know in the literature, everything we found before, the degeneracy is fine. And the same for the intercept. So those are the numerical data, and now we can match it with the dashed line that is the interpolation given from ABBA solution, and is matching perfectly, and everything is fine. Obviously, we can push to very high order. So we can go, for example, L equal to 30 if you want. And this is a very high order solution. There are 225 trajectories. And you can really go wherever you want. And more bigger is L, obviously, more precise is the computation. Indeed, this expansion is exact up to the power G to the 62. So pretty high order. Okay, so I guess I'm kind of...
Michelangelo, sorry,
Yeah.
can I ask a question? So these degeneracies are, sorry if I missed it. Is there an independent prediction of before you counted them from your Baxter equation? Was there an independent way to count them?
The numerical, all the numerical data that I gave you before is totally independent because, I mean,
but without integrability, I mean, some other argument, okay.
No, there is no argument that is telling you how many trajectories are bending.
And the degeneracies, so here, for example, in this figure, there are these intervals, right? So
yes,
the degeneracy is the same in these various subintervals?
Yes, it's the same because on top of the same horizontal trajectory, obviously you have those segments and they divided by branch points. Okay, so here there is a branch point, there is a branch point, and so on. What is happening in the interval in the middle, the one that we were looking at before, for example, is the same that is happening here because there is no dependency in the equation on the position that you are on top of the horizontal trajectory. So it has to be the same up to infinity. And this, we have very good match with numerical data.
Okay, thanks.
Okay, so I guess I'm kind of out of time, or can I have 3 minutes more since we had problem at the beginning?
Yes,
Yeah.
If you don't mind. I just want to say something like 2 slides more, because indeed, now we were talking about just the horizontal trajectory, and so we can solve everything on top of the first horizontal trajectory. But an interesting point is that at some point, the horizontal trajectory is meeting the D-clap area, so where the trajectory is diagonal. So what we want to see is there a way that we can use this ABBA result to know something about the bending point? And the answer is yes, indeed. And indeed, let's give you an example because in general is more complicated, but let's say, let's fix L equal to 3. And the ABBA result is giving this expansion up to G to the 4. Fine. This is in terms of chi. And another interesting stuff that I didn't say is that higher order contains the dependence of delta just in chi again. So just in the BFKL Pomeron or derivatives of it. So for the whole ABBA expansion, delta enters only through the BFKL Pomeron eigenvalue or derivatives of it. And that's pretty nice. Okay, anyway, let's go back to this example. Let's take the L equal to 3 case. Let's zoom close to the edge, so close to the bending point where the two trajectory meet. And we can re-expand these variables and we find this expansion. Fine. And then we see, for example, at our numerical data, we can see that 3 trajectories are playing a role there. You remember for L equal to 3, there are 3 sheets that are playing a role close to the branch point. So we can say, let's build a generic order 3 polynomial, and let's check the coefficients inputting the data that we have. And we find this polynomial that we can solve in terms of D, and we have this expansion in poles. Omega is S plus 2. And this is matching exactly what is known by literature by like almost 20 years. That's fine, but more interestingly, I want to show you like pictorially what is going on. If we plot this polynomial, we see those resolution, let's say, of the branch point. The branch point is somewhere here, but outside the screen because it's in the imaginary side, okay? And if we go numerically very close to the branching area, we see exactly the same behavior. And that's pretty nice because just with the ABBA solution that is valid very far from this point, so in this area, we can know how those trajectory bends. And we can go L equal to 4, and you see those dotted lines are actually this, what we call this branching regime is interpolating super nicely in the turning point and also away from it. So this is pretty surprising. And there are just 2 curiosities that I want to tell at the end, is that the number of trajectories that are actually playing a role here in this branching area is exactly the same number of local operators at S equal to 2. We don't know why, but if you count the number of operators at S equal to 2 for the twist, for example, twist 4, the same number of trajectories will bend. So this is what we saw from our data. And another important curiosity is that the leading pole, so if we are expanding in omega, as I was showing before, the residue of G square over omega, so this term here, this number, is exactly the same of the one loop anomalous dimension of the operator that are S equal to 2, for some reason. We don't know why. But we check it up to very IL, so we are pretty confident that this is true and this is general, but we have no motivation to believe why. This was just a couple of curiosity. Anyway, so I can flash a couple of open questions. More importantly, I mentioned a couple of them. Could be nice to understand this whole business from QFT point of view. So understand which kind of light ray operators are behind this business and how let's say how we can rewrite ABBA in terms of light ray operators point of view. And then could be nice also to understand the analytical continuation in the declap area, the diagonal part between the local operators in general. And the easiest open question is how can we explore the lower horizontal trajectories and how we can remove some symmetry restrictions. And this is something that we are working on now. And these are just to show like numerically what is going on. This is the L equal to 2 case. You see that the general C1 first horizontal trajectory, then there is a second after it. But this is way more degenerate, way more complicated, so everything is more involved there, but we have a new version, let's say a ABBA 2.0 to solve also for the second horizontal trajectory and so on in principle, okay? So I can stop here, I guess. Thank you.
Oh, I guess we have time for one quick question.
May I ask a question?
Sure.
There is an old problem that if you go to high twist, then if you start with local operators, you can diagonalize them and find multiplicatively renormalizable operators. But it's not known how to continue them analytically to produce Regge. How to continue them analytically and find the structure of these operators in the Regge limit. It is an old problem, which is, I think, we now found solution. For the anomalous dimensions, yes, for the spectrum, it's normal more or less what's happening, and that's what you're doing. You have this nice work. But my problem is that basically for eigenfunctions, that we need not only the eigenvalues but eigenfunctions.
Mhm.
And that's actually a big problem. So can you see some possibility to go in this direction?
I mean, you're interested for higher twist stuff, so L very big.
Yeah, because if you have three particle already, if you have three particle local operators, you have a big spectrum of anomalous dimensions, and just starting from the spectrum of anomalous dimension local operators, you don't know how to continue analytically.
So I mean, like
I think this analytic continuation should be uniquely defined by unitarity of the 3 points of the 6-point amplitude, but nobody ever was able to solve this unitary condition. But you might have some explicit solution in this case.
I mean,
Yeah.
Google.
Mm.
I mean, from our side, when we talk about like a larger operator, we are talking about larger operator of this kind, like trace of a derivative of S z to the power L, in the case I show you now. But it's also true that we can relax many symmetries, so we can relax parity symmetry and so on. We will have many degeneracy for local operators in the, let's say, D-club area. In principle, we know how to continue all of them, because the only changes that you have to do is the ansatz for the P function from a QSC point of view. So in this related problem, let's say this QSC word, quantum spectral curve word, just relaxing some symmetry between the P and Q function will solve the problem. But I'm not sure that is what actually we are talking about here, because indeed from let's say region point of view, I'm not sure that relaxing all of them, even if L is big, will represent an exchange of more than 2 regions. So higher exchanges of regions, I'm not sure that this is the same analytic continuation that we are doing. I guess in the analytic continuation we are doing, probably we are looking at just 2 of them.
Oh, well, okay, so but I'm saying that it's just your eigenvalues, they lie on some very complicated Riemann surface in general, right? And you have an idea how they move along this Riemann surface, and that's what you're calculating. That's quite
Yes.
nice, actually. But in addition to eigenvalues, you have also eigenfunctions.
Yeah, I understand what you mean.
This is the problematic part.
Yeah. Let's say from numerical point of view.
Three clones, I mean, this is, I don't know whether they will mix somehow, but yeah.
Yeah. No, I see your point. I mean, let's say the best case scenario that we have now is to generalize to any kind of operator, obviously in the same kind of business. So we just look at the anomalous dimension, or if you want the spin in terms of the anomalous dimension, that is more convenient in our case. But in general, I don't know if we can build an entire set of equations to fix again functions also. This I don't know.
Okay, so I would propose to ask further questions in the discussion session, and let's thank Michelangelo again.
Thanks a lot.